So let me summarize what we've done so far. So just by reflecting on Kiley paths and without having to look at the particular geometrical interpretation that we have in mind, we've been able to see that the set of all Kiley paths, ignoring the center, can be decomposed into the set of right paths, left paths, up paths, down paths, where what I mean by that is just the first step in each path in R is right, the first step in each path in L is left, and so forth. So that's an easy observation. The second observation we made is that if you put together the set of all left paths with the result of applying the arrow operation to the set of all R paths, then you get back the set of all paths. And similarly, if you put together the set of all up paths, put it together with the result of applying the arrow operation to the set of all down paths, you get the set of all paths. So that's great. Let's now see how we can use these results to get back the proof that the set of endpoints of Kiley paths implemented geometrically can be duplicated in the way that was described earlier. So because the object we want to duplicate is not quite the set of Kiley paths, but the set of endpoints of Kiley paths, we need to somehow get from this result to this result. The result that the set of endpoints of Kiley paths can be decomposed into the set of endpoints of right paths, endpoints of left paths, and so forth. Whether or not that's true does depend on the geometrical implementation of the paths that we have in mind. But given the one that we've been discussing that lives on the plane, this actually does turn out to be true. The reason it's true is that every Kiley path has an endpoint distinct from the endpoint of every other Kiley path. In fact, it's for that very reason that we needed to decrease the distance that each step traveled. Because had we not done that, then, for example, an up right path would have had the same endpoint as a right up path. So it's precisely to get this result that we made that restriction. Now, similarly here, the results that we really need, because we're interested in duplicating the set of endpoints of Kiley paths, is this, and similarly that. Fortunately, it's very easy to get from here to here. All we need is the observation that every Kiley path has a unique endpoint, and that will certainly be true on the geometrical interpretation that we've been considering. Now, to complete our proof, we need a third point. To complete our proof, we need the observation that in order to get from the set of endpoints of right paths to the set of endpoints of the result of applying the arrow operation to R, all we need to do is perform an expansion plus a translation. It is thanks to that fact that we can say that you can get one copy of CE by putting together LE with an expanded and translated version of R. And because of an analogous statement involving D and U, we're entitled to say that you can get CE by bringing together UE with an expanded and translated version of D. So if we look at the animation, we'll see how that's supposed to work. So the figure on the right shows what happens when one translates and expands R, and the figure that's about to go to the right shows what happens when one translates and expands U. We can get rid of that for now. Notice that the fact that the arrow operation corresponds to this geometrical operation depends entirely on the particular way in which we've chosen to implement the Kiley paths. The way we're going to prove the Banach-Tarski theorem is by considering a version of the Kiley graph where instead of thinking of paths as moving across a plane with upright left down just corresponding to upright left down movements on that plane, what we're going to do is we're going to take a ball and we're going to think of the paths as occurring across the surface of the ball. In particular, we're going to think of up, down, left, right steps as rotations. Up, down steps are going to correspond to rotations about the x-axis, and left-right steps are going to correspond to rotations about the z-axis. So same collections of Kiley paths, different geometric interpretations. And because the interpretations are different, we need to make sure that the transition from here to here and the transition from there to there remain valid. And as it turns out, they will remain valid. It's not trivial, but we will see that it is indeed the case. So we're going to pick our angles of rotation carefully with the result that different Kiley paths always have different endpoints. That's going to allow us to get from here to here. And we'll be able to get from here to here for the same reason as before, that every Kiley path has a unique endpoint. Now, what about that? What about result number 3? Well, result number 3 depends entirely on the geometric interpretation that we give to the set of Kiley paths. When we interpret them as living on the surface of the sphere, we simply do not get that result. But we get something even better. So what we get instead is that to get from here to here, all you need to do is to perform a rotation. And similarly, to get from here to here. So in other words, if you have the ball and you look at every point on the surface of the ball that is the endpoint of some Kiley path in R, there is a particular rotation that you can perform, which is going to take you from that set of endpoints to this set of endpoints, the set of endpoints of all paths in R arrow. And similarly to get from there to there. And this is incredibly beautiful. Remember that the reason our warm-up case 3 was a bit of a cheat is because when we decomposed the object into different pieces and reassembled them, we allowed ourselves an expansion, 2 expansions, in fact. When we implement the Kiley graph differently, when we implement it geometrically on the surface of the ball with these rotations, we're not going to need expansions anymore, because to get from here to here and from there to there, all we need is a rotation. So what we get is that we can take the set of endpoints of the Kiley graph as distributed around the surface of the ball, decompose it into quadrants, and get 2 copies of that set simply by putting together one of the quadrants with a rotated version of another, and that set of endpoints with a rotated version of this set of endpoints. So we will get the real thing. Stay tuned for the details.